Okay, so we will start today with oblique collisions. Of two particles. Or bodies. Okay, so in general, if you have this kind of situation, suppose we have this situation, this one is coming in at some velocity v0 and it hits another body m2 which is at rest. Okay, and on impact, situation looks something like this. The line of impact is the center to center line. So the collision impulses, they act like this. And as a result of that, after impact, what happens is that this body will develop a velocity along the direction in which the impulse acted for it. Okay, whereas this body's direction of motion will change, become something like this. So they will set off in different directions. Hence, it is an oblique collision. So in general, what will happen here is there will be conservation of momentum. But that will become a vector relation here. This is the initial momentum. So this is vector relation, and coefficient of restitution and we will require these to solve the relation. Okay, so just note down up to here first. Done. Yeah. So now how we do the momentum conservation, I mean, how we express the components, etc., can vary a bit from question to question, depending on what kind of information is given. So let's understand this with some examples.
Hello.
Done, right?
Yes.
Okay, so let's start with the first level example. So in this, what is happening is a particle like this with an initial velocity like this comes and hits something which is comparatively larger in size, which is at rest. And what is observed is that after impact, after impact, this one has a final velocity which is perpendicular to its initial velocity. Whereas the second one has a velocity along this line. So after impact, the first particle, small m, is deflected by 90 degrees. So what this statement means that it is deflected by 90 degrees means that its final velocity v1 is perpendicular to its initial velocity. Okay, and this angle here is also given to us. This angle is 37 degrees. Okay. So if v0 was 12 meters per second, v1 is 4 meters per second, small m is 1 kg, and capital M is 4 kgs. Then we have to find the value of v2. Okay, so this is the easiest level question because you can see a lot of information is given. Okay. The directions of both the final velocities are given, v1 and v2, in terms of the initial velocity's direction. And the magnitude of one of them is given. Okay, so ultimately, the only information that we require, in fact, there's too much information given in this question. So let's say capital M is also unknown. So we have to find v2 and we have to find capital M. So two unknowns. Okay. So how we will solve for these two unknowns is we will apply conservation of linear momentum. Which will result in two equations because there are two components. And to apply that vector relation, okay, what we'll do is we'll take V naught as 12 I cap, and therefore V1 as 4 J cap. Okay, so just write the momentum conservation equations according to this choice of axis which I've hinted over here below, and you will get the required relations. Okay, so let's check out the answers. Jitesh and Jinendra. Yes, that's correct. Okay, so first of all, let's understand the system of axis that I've talked about here. So what I'm doing is I'm taking the direction of this one's initial velocity. This axis I'm taking as my x-axis. So that automatically means that my y-axis becomes along the direction of the final velocity. So my momentum conservation equation, when I write it, becomes very simple. Okay, let's check out the values. I'm just writing down the equations. So theta is 37, V0 is 12, V1 is 4. Or small m rather, instead of small m is 1 kg. Okay, so we have small m V0 is equal to small m V1 plus capital M V2. So when we write this in component form, this will become m V0 I cap is equal to m V1 J cap plus this V2 will have components of cos 37 I cap minus sin 37 J cap. So we have this relation. Cos 37 is 4 by 5. Okay. And sin 37 is 3 by 5. Okay. So when you look at this equation and compare the components, you can see that this is one equation we'll get. This is the second equation we'll get. So now it is a matter of solving these. Okay. So from equation 1, we can substitute 12 as 4 by 5 capital M V2. And from equation 2, we can substitute so this is not the information here is inconsistent, right?
Yes.
It is not really giving us anything conclusive. Okay, let's change the data in this question. Okay, so there's an issue with the data in this question. The data is not consistent. As you can see, from equation 1, we are getting MV2 as 15. Okay, and from equation 2, we are getting capital MV2 instead of as 15, we are getting it as, okay. So first of all, what we will do here is we'll change the data that is given. Okay. The data is inconsistent. Okay. So we will change the data given versus the data asked. Okay. So let's say the mass is given to us, but V1 is not given. So we want to find V1 and V2, both the things. So only the directions are given. Okay, so now let's see how the question works out. Okay, so the equations still are same, but now when we substitute from equation 1, we will get 1 into 12 is equal to 4 by 5 into 4 into V2. So V2 will come out to be 15 by 4. Okay. And from equation 2, so we will get V1 as 9 meters per second. Okay, so just make a change in the data of the question. I'm just going back to that. Then I'll come back to the solution. So what I've changed is this, that I have kept I've kept V1 unknown. Okay, and instead given the mass of capital M. Okay, so let's work this out. So this is how it's coming. Okay, now we will do one more interesting calculation in this question. We will calculate the value of coefficient of restitution. So we'll see that from the given data, not only can we calculate V1 and V2, but we can even calculate the coefficient of restitution. So let's see how that works out. Okay. So first, just go through this part, the conservation of momentum. So just application of conservation of momentum is giving us the solution to the first part, which is V1 and V2. Two unknown quantities, so two equations required. And those two equations we are getting from the individual components of the momentum conservation equation. We are getting one equation for conservation of momentum along x-axis, which we have taken as the direction of V0. And we're getting one more equation for conservation of momentum along the y-axis, which we are taking as the direction of V1 or the line perpendicular to V0. Okay. Okay, so note this down, and also now try to visualize how we'll get the value of coefficient of restitution. So once again, when we define coefficient of restitution as separation velocity upon approach velocity, so two bodies or two particles in this case moving in random directions, what is the instantaneous approach and separation velocity? It is the
So,
direct, it is the component of the relative velocity along the center to center line or along the line joining the two particles. So that is the interpretation that we will use for approach and separation velocity. Yes, any doubt?
means I didn't understand how we got the first and the second equation.
Okay, so we are conserving momentum now. So the first equation, acha, how we got it from, you've understood how we got the boxed equation, no?
Yes, sir, I got it.
So उसमें just compare the I cap and J cap na on both the sides. Understood, na? So what is the X component, the I cap component on the left hand side? It is MV0. On the right hand
Yes,
side,
sir.
it is 4 by M cap, 4 by 5 capital MV2. So they should be identical.
Okay, sir. Okay, got it, got it.
And on the, for the Y
Yes,
component, left hand side is 0. So right hand side.
got it.
Okay. Okay, so let's understand how the coefficient of restitution will work out. Yes, I'm getting some answers. But first of all, there's some doubts that people have asked, so let me explain that. In oblique collision of particles, only component coming face to face is changing, right? No, the component changing depends on the direction of the impulse actually. I'll explain this point, Jitesh. Achha, you mean the normal component by that? Face to face means normal component, is it?
Yeah, the ones
Yeah,
who
that is correct. Okay.
these component which are coming face to
Yeah.
face.
So only the component of momentum which is along the line of impact, that is along the line along which J is acting, that one will be changing.
Yes.
Okay. And no, J and V will not be in opposite direction necessarily, yes. Okay. But it's like this. So let's first just compare that collision diagram. Then we'll come to coefficient of restitution and all that. So I'll explain what I'm trying to say here with this diagram. So suppose this is the situation just before impact, just before the particles are coming in contact. So this is the direction in which this particle was moving. Now, as they come in contact, what happens is that the contact force is going to be like a normal contact force. So normal direction, normal reaction force will always be along the direction which is perpendicular to the tangent, no? Perpendicular to the plane of contact. So that's the tangent line. So that will be along this line. So this line over here is the line of impact. It is a normal, whereas this is the tangent at the point of impact. So the impulse will act along this normal direction because it's basically a normal reaction force. So the impulse will act like this. Okay. So for the first particle, you can see that final momentum is equal to initial momentum plus impulse. Okay, this is a concept that impulse is equal to change in momentum. So impulse acting on particle 1 because of 2, it is equal to the final momentum minus the initial momentum. This relation. So this we've expressed like this over here. So when we think of this like a vector diagram, this was the initial momentum. This is the final momentum. So the impulse is like this, the initial momentum plus the impulse. Like this. Okay, this is the impulse acting on. Like this. Okay. Whereas for the second one, the impulse itself is equal to the final momentum because the initial momentum was 0. So that is why we have that sort of direction. So you'll see that if you just add these two equations, you get the momentum conservation equation. So that's unnecessary, but this is just to explain to you the relationship between impulse and momentum. So that is why this, in the final picture, the second one goes off along this direction, along that center to center line. Whereas the first one goes off in this direction. Okay, so this angle actually is given to us indirectly. If you see, this angle is given to us because the direction of V2 is given. This angle theta is 37. So this angle is known to us. So that is what we have to use in the approach and separation velocity also. Okay. So make sure you understand this diagram. Now we'll talk about approach and separation velocity. So again, this is the picture before impact, just before. So approach velocity will come from this. Can you tell me from this what is the approach velocity?
V not only, sir.
Me not only. Yeah.
No, why we not?
Yeah,
It
because
has to be the component of relative velocity along the direction joining the two particles, no?
V not cos theta.
Yes, so it is V naught cos theta beta. So approach velocity is V naught cos theta. It is the component of relative velocity along the line joining the particles. That is the center to center line. Just at the time of impact. That is the approach velocity. So similarly, in this diagram, what is the separation velocity?
So first we'll have to find the relative velocity of V1 and V2, then we can find it.
Yeah, so we'll have to divide V1 in components here. V2 is already in the correct direction, no?
Yes.
Sir.
So V2 is already along the center to center line. But V1 is the one whose components we'll have to make. Okay. So V1 is in this direction. So from this diagram, you can see what is V1's components. V1 cos theta in this direction.
Yes, sir.
And V1 sin theta in this direction. So along the center to center line, V1 has a direction opposite to V2. To the center of the other one. So from this you can see what is the separation velocity. It is V2 plus V1 sin theta. Is this clear?
Yes.
Yes, sir.
Okay. So now our coefficient of restitution will become the ratio of this separation velocity to approach velocity. So it is V2 plus V1 sin theta upon V1 cos theta. So V naught cos theta. Okay, so how much had V2 and V1 come? V2 was
9.
3.75 something. Huh?
V2 was 9, V1 was 3.1.
No, V2 was 3.7.
V1 was 9, no, beta?
Yes, sir.
Yeah, Vedant.
That's okay. Yeah, so we had got V2 as 3.75, V1 as 9, and theta was 37 degrees. So 3.75 plus 9 into sine theta, which is 3/5, sine 37, okay, divided by 12 into cos, that's 4/5. So 3.75 plus 5.4 divided by 9.6, ऐसा कुछ आ जाएगा ना? So we're getting a pretty large coefficient of restitution, isn't it? We're getting 9.25, is it? No, 9.15 divided by 9.6.
Yes, that's something 0.9.
So it's pretty close to 1. It's almost an elastic collision. Okay, so hope this application is clear.
Yes, sir.
Okay, now let's look at a couple of more relatively simple questions. Like this one, coefficient of restitution was little complicated, but the first part, finding out the final velocities, that was quite easy. So that is a JEE Mains level question. So let's look at another one like that before we come to the more typical type of examples. So A and B are identical particles. Okay. After impact, A's final velocity is at theta equal to 30 degrees with respect to its initial velocity. And B's final velocity equals to V1. Or let's say it has the same magnitude as VA. So if V0 is equal to 10 meters per second, and find the magnitude of the collision impulse. Okay, so this one is a relatively simple question. Just try it out. Just make the diagram and understand the vector relation for momentum conservation, and you'll see again momentum conservation is enough over here to solve the collision itself.
Sir,
Yes.
sir, in your diagram, you have shown that the V0 ka plane is not in contact with B. So, like, if this kind of situation comes and we are given the distance between them, then we have to take the initial velocity of B something, right, to reach that position.
No, B is at rest. Just place it such that they are coming in contact. Okay. Yeah, but if you have a situation where B is also moving, then you'll have to take that into account. Okay?
Yes, sir.
Sir,
Yes, very good, Janendra. Your answer is correct. VA and VB will have a magnitude of 10 by root 3 each, or you can write that as 10 root 3 by 3. And both of them will be at 30 degrees each from the initial velocity of V naught. So the angle between them will be 60 degrees. So the collision picture will look something like this. From this initial situation, what will happen is after impact, this angle is given to me as 30 degrees. If I take this angle as theta, so momentum conservation gives me that mv naught is equal to mv1 cos 30 degrees plus mv2 cos theta, and 0 is equal to mv1 sin 30 degrees minus mv2 sin theta, and v1 is equal to v2. This is given to me. So when we use that, yes, very good. So from equation 2, and substitute that in equation 1. Okay, so this kind of value. And now we can see the impulse. As a magnitude of the final momentum of the second body. So the mass is 2 kg and this becomes a collision impulse.
Sir, the collision is affected by the geometry of the particles also, right? Or it's
Yes,
just comparing
it
the
is affected. Like here we are taking round bodies, okay. But for example, if a particle comes and hits a triangular wedge like this, then the impulse's direction is affected by this, no?
Yes, sir. So like we have to apply their partially rigid body and then convert all
Yeah.
this.
But see, then what happens is, now generally, if you take that type of collision, it is collision between two separate rigid bodies. And there may be also what we call transfer of angular momentum along with linear momentum. So the bodies may not only translate, they might also spin after impact. Like in an extreme case, if you take a particle coming and colliding with a rod like this, and it's not colliding with the center of the rod. So then what will happen is, after impact, the rod will go into that kind of motion, it will be spinning.
Yes, sir. Yes.
Okay, so that we will look at in rotational mechanics chapter, which is the next chapter we'll do after this. So there
Achha.
also we'll continue with collisions, but in those collisions, we'll see that along with linear momentum, we'll also discuss about angular momentum.
Okay, sir. So now we are interested in round spherical stuff, but later on we
Yeah,
might.
correct. Now we are basically looking at collisions between what we can treat like particles. So round objects like this colliding such that the impulse is along the center to center line. So it doesn't create any angular motion. So that situation can be treated like particles.
Got it.
Okay, now we'll come to the slightly more complex type of examples. Okay, these two examples were more or less simple examples at JEE Mains level, but at advanced level, we have a little bit more complex concepts. So the first is we'll discuss a sort of a theorem, but we will discuss it as a proof of the theorem. For example, this thing is given in H.C. Verma also as one of the questions which you have to, the question is posed like a proof question. It's not given as like a theorem in the theory part. Okay. But we have to remember the result of this theorem I'm talking about next, because it's important to solving those type of problems. Okay. So that theorem is the following, that if two bodies or particles of identical mass make a perfectly elastic oblique collision, okay, then their velocities after impact are perpendicular to each other. But this is in the situation where the first body impacts the second one at rest. So what the theorem means is that if a moving body comes and hits a stationary body, but they are of identical mass and the collision is perfectly elastic. So if this situation happens, oblique impact, and E is equal to 1 or perfectly elastic, then by definition what must happen is, after impact, the two bodies must have final velocities which are along perpendicular lines. This angle here has to be 90 degrees. So let's look at the proof of this. So E is equal to 1 also implies that kinetic energy is conserved. There's no dissipation of kinetic energy. So half m v naught square is equal to half m v1 square plus half m v2 square. So this gives us a second equation. Now when you compare these two equations, you should be able to realize immediately. Because from equation 1, you can see that okay, and from equation 2, so comparing these two, you can see that mod of v1 plus v2 vector sum is equal to square root of v1's magnitude square plus v2's magnitude square. So that means v1 is perpendicular to v2.
Yes.
So this is an important theorem that you should remember. This is one way of proving the theorem. We will see another way of proving this also in a bit of time. Okay. When we discuss a little bit more about coefficient of restitution application. So just make a note of this theorem first.
Done, sir.
Right. So this theorem can be then directly used in these type of questions. Okay, let's do an example. So now we will come to a slightly more tricky type of question, which is, you can say, a JEE Advanced level question. So in this one, some information is given indirectly about the collision, and that information will be like this, that let's say these are two spheres or two disks of identical mass but slightly different radii, as you can see. Okay. And the first one is moving with a velocity whose line of action is this one. So this velocity is along this so-called line of action. Now if we draw the center of B, this line of action is at a perpendicular distance. Now that perpendicular distance is given a special name. It is called collision parameter or impact parameter. Okay, so first of all, A and B are disks like carom coins on a smooth horizontal surface. With mass of A equal to mass of B. But their radii are different. Radius of A is 2 millimeters and radius of B is 3 millimeters. So they are made of different materials. That's why even though the radius is different, their masses are the same. Okay. B is initially at rest. And A makes an oblique collision at velocity V0 such that the impact parameter D is equal to 4 millimeter. So what is the impact parameter? By definition, the impact parameter is equal to the perpendicular distance of the line of action of this particle's velocity V0 with respect to B's center. So that is how we define that impact parameter. Okay, so that is given to us as 4 millimeters. Okay. So if V0 is equal to 12 centimeters per second and the collision is, sorry, make it 15 centimeters per second, to be easier. And the collision is perfectly elastic. Then find the final velocities of A and B, both in magnitude and direction. Okay, so remember, two conditions are there. The collision is perfectly elastic and the masses are equal. So we can make use of the above theorem that we discussed. So making use of that theorem will save you a lot of time in this question. Okay, otherwise also you can solve it, but you will kind of end up proving that theorem again through your solution.
Sir,
Okay, very good, Junaid and Vedant. So can you tell me the angles at which the final velocities are with respect to? Okay, I just
It's
to restart that program. Okay, just give me a moment. Or what is the angle of impact? That is the
Sir,
thing.
the angle of impact with the center of line of V naught was 53 degrees.
yes, sir.
Yes, very good. Okay, so it will be basically sine inverse of that impact parameter divided by the sum of the radii.
Yes, sir.
That is the
Yes.
concept we have to use here. Okay, so that was the geometrical part of the question. That in addition to the collision thing, how we make use of the geometry which is given. So if this is the situation just before impact, let's say. Okay, so we will compare before impact, during impact, and after impact. So before impact, just a second, I'll reshare that file. Yeah, so before impact, this initial velocity vector this line of action is at a perpendicular distance from this one's center equal to that D parameter, that impact parameter. Whereas the center to center line, this one will have a magnitude of R1 plus R2. So if this angle is theta, so you can see that the collision impulse will act along that. So this angle theta in this diagram, you can see that sine theta is equal to D upon R1 plus R2. Now the way that is given, that works out to be 53 degrees. Okay. Now since the masses are equal and the collision is perfectly elastic, additionally we know one thing, that if this angle is theta, then the angle at which the final velocity of this one goes will be at 37 to this line, right? Because they have to be perpendicular.
Yes.
Yes, sir.
So V2 has to be along the impact, the line of impact, or the line along which V0 is or J is acting. Okay. But in addition, now we also know that V1 has to be perpendicular to V2 because the collision is perfectly elastic. So making use of that really helps over here. Because know that this angle is theta. Now this angle will be 90 minus theta because V1 must be perpendicular to V2 because E is equal to 1 and M1 is equal to M2. So that helps us understand now that. So once we understand that this angle is 37 degrees and this angle is 53 degrees, now the problem becomes really simple to solve because we understand that MV0 will become equal to MV1 cos 37 plus MV2 cos 53. So this equation will give us one relation, and we have 0 is equal to MV1 sine 37 minus MV2 sine 53. Okay, so just these two equations are enough now to solve this. So from equation 1 and 2, we can see from equation 2, we can see that V2 is equal to 3 by 4 V1, correct? And from equation 1, we can see that 3 by 5 V1 plus 4 by 5 V2 is equal to V naught, which was given to us as how much? 15. Okay. So this is equation 2, equation 1. So we'll just substitute this here. Four by 5 into 3 by 4. Okay, so is this equation correct? Yes.
Yes, sir.
Or whatever, centimeters per second. Okay, and then V2 becomes okay, so this becomes the easy way of solving this question.
Sir, it will be 6 by 5 even, no?
Yes, sir.
Which one? Which equation?
Just
Sir,
the
not
last
9 by.
It will be 3 by 5 even plus 3 by 5 V2. So it
Oh,
will
sorry,
become
sorry. Yeah, my mistake. So this will be 6 by 5. Yes. So this will become 25 by 2, is it? So final value of V1 you are getting 12.5. Should be getting this as 9 actually. Something has gone wrong in our calculations. Just a minute, huh? Let me check this. So what we should be getting here is that V2 should become 9.
So,
Yeah.
so I did it in a way like if E is equal to 1, then V approach is equal to V separation.
Yes,
So
sir.
we know V approach as V naught cos theta, and V separation will be VB.
Sir,
And then
Yeah,
from
so
the
this
theorem we
equation
get
correct. That is also correct. Okay, so that result should give you the same as this.
from the
but
theorem
in
I
that
took V naught is equal to VA plus VB. Is like that.
VA plus VB. What are VA and VB?
V1 plus V2, right? That.
Okay, I mean vector sum, that way you do.
Yeah, yes. Sir.
Okay, yeah, so that should give us the same result. So let's just check what has gone wrong here. So we have taken 53 as this angle, so that's okay. So equation 1, let's check again. So this is 37 and this is 53. So I think the values have gone wrong here. Cos 37 is 4 by 5, no? And cos 53 is 3 by 5. Okay, so that is where this has gone wrong. Okay. This equation is incorrect. What about the first one? Is it correct? No, that's also wrong, no? Because that's okay, because sine 37 is 3 by 5 and okay. So first one is okay, second one just taken the wrong values. So cos 37 is how much?
4/5.
4/5. So 4/5 V1 plus cos 53, which is 3/5 V2, is equal to V0, which is 15. That should be the first equation. So now when we substitute this here, we'll get the correct value. So 4/5 V1 plus 3/5 into 3/4 V1 will be equal to 15. Okay. So we have 4/5 plus 9/20. So 25/20 V1 is equal to 15, or V1 becomes 4/5 into 15, which should be the case. Okay, V1 should be equal to
Yes.
V0 sine 53. So that's 4/5. Yeah. So V1 will come out to be 12,
Yes.
and V2 will come out to be from this 9. Okay.
It's the same we could have done with coefficient of restitution also, right? We
Yes.
separate.
Yeah, but see, the thing is, we have to understand the logic of why V1 is perpendicular to V2. Achha, after using that theorem you're saying, we could have used coefficient. Yeah, we could have done that also. But here in this diagram, we can see that the separation velocity is how much? It is directly just V2, because this is perpendicular, na? This angle is 90. So therefore, here we can see that the approach velocity is how much? It is V0 cos theta. So we could have used this also, that V separation is equal to E times V approach, and E is 1 here. So V2 is 1 into V0 cos theta. So that would have directly given us V2.
Yes.
So we can do that also. Okay. Okay, now we'll just take another 5 minutes to understand that how to develop a more general case here. What if the coefficient of restitution wasn't 1? Or what if the masses were not equal? Or both the things put together, how we'll solve? Okay. So let's see this same situation now, but with, let's say, different value of masses, okay, as well as different value of coefficient of restitution. So that is the maximum complexity level of question you can get for this type of oblique collision. Okay, so our next example, let's say given that A and B are of different masses apart from being of different radius. So given this time, let's take D as 3 millimeters and R1 again as 2 millimeters, R of B as 3 millimeters. And let's take the masses in that ratio. Or let's say the mass is proportional to the area. So 4:9 kind of ratio. So, okay. And coefficient of restitution is 0.5. Let's say. Okay. So same situation, but with different masses and different coefficient of restitution. So we have to find the final velocities. Okay. So here we will have to make use of the value of coefficient of restitution. Okay. So for that, what we'll do is, okay, so note that since value of E is given, okay, to use the equation E separation is equal to V approach, okay, we need to resolve the velocity vectors such that the line of impact that is the center to center line, is one of our axis. So let's say that we take as our x-axis. So instead of taking the v0 velocities direction as our x-axis, what we'll do is we'll take the center to center line as our x-axis. Okay. So here we will take this line as our x-axis while solving. So what this means is that take this angle, take this line take this as our x-axis and take this as our y-axis. Okay, so this will be the easy way of solving the problem so that we can use the coefficient of restitution easily. Okay, so just make the diagram and give this a moment to work out the equations. I will give this a minute to work out the equations. I'll put them up.
So we have to take the same V0 as previous problem, right?
Numerically, you can take that same value, V0 as 15 centimeters per second. But notice that D is different. Okay, D was 4 millimeters there, it is 3 millimeters here.
Yes.
So make sure you adjust that. So now that theta angle will become how much?
37 degrees.
Yes, it's become 37 degrees. Okay. Now, here we have to be a little careful. Our V2 will not be V0 cos theta because there's a coefficient of restitution involved and the masses are different. So we have to be a little careful when we are solving. You understanding the point?
Yes, sir.
Okay, so let's look at the geometry of the collision. So now we can again understand that this impact parameter being D and this being R1 plus R2, we can see that theta is sine inverse d upon r1 plus r2, that over here becomes sine inverse of 3 by 5. So our theta is 37 degrees. Okay, but the masses, remember, are not equal anymore. They're different masses. So the final velocities will not be perpendicular to each other because the masses are different. So let's say this one's final velocity will be along this line only, BB. But
sir, I
this
got
one's
that
final
from
velocity is along some direction like this, let's say, which is not along that perpendicular. So let's say now this angle is some alpha, let's say, because, but we will still take the same system of axis because we need this thing. Huh? We need to apply the coefficient of restitution term. Yeah, what were you saying, Vita?
Yes, sir, I did the same thing. I took the coefficient of restitution equation and from that I got VB. Like
Okay,
VB.
okay. So E is 0.5, right? And mass of A is 4 kg, mass of B is 9 kg, right? Okay. So first of all, let us see here, what is the approach velocity? That is V naught cos theta. Okay, and V naught was 15 centimeters per second. So that is becoming 15 cos 37. So that is now becoming 12. Approach velocity is 12. But according to this diagram now, what is our separation velocity?
VB plus
Yes, very good.
VA's component in the negative x direction.
Very good. So this angle should be how much? I mean, if I have taken this angle as alpha, then this angle is also alpha.
Yes.
Is it?
Sir, yes.
No, we can't say that
Sir.
angle is alpha. Okay. So, I mean, that angle and this angle are not the same. So let's just take that angle as alpha. Okay. No, because VA need not be perpendicular to this line. So,
yes.
no, so, but let's take in our diagram that angle is alpha. So then this will become VB plus VA.
VA cos alpha.
Cos alpha. Okay. Because this is what we can say is the normal component.
Yes.
Okay, of VA. Because we can see that this x-axis is the center to center line. So this is the normal line. And the y-axis is the here the y-axis, this one is the tangential axis. Okay, so this is the tangent. Okay, so VA sine alpha here, this is the tangential component. So we'll come to that also. Okay. Now, what can you tell about the tangential component of VA? Okay, I will just make a claim that tangential component of VA should be conserved. Now, can you tell me why?
So because it is perpendicular to the line of action of this.
Yeah, tangential component of VA should be conserved. Why? Because the impulse is acting
in the normal side.
In the normal direction only. That means there is no impulse on A acting in the tangential direction.
Yes.
Okay, so that's one thing. So one thing we can directly see over here, before we worry about E and all that, we can see is that the tangential component VA sine alpha should be equal to the tangential component here, which is how much? Okay. Which is V naught?
V naught sine 37.
Sine 37.
9 centimeters.
Okay. So we'll come to that. Okay. So let us write the conservation of momentum for the system. So you can see that MA into V naught, okay, cos theta I cap plus sine theta j cap, because remember this is our y axis and this is our x axis. This quantity should be equal to, in the final diagram, MA into VA into minus cos alpha I cap plus sin alpha J cap plus B's momentum, which is now MB VB I cap. Okay, so when you pick this together, you can see that this is MB VB minus MA VA cos alpha I cap plus MA VA sin alpha J cap. So when you see the J cap component of this equation, you realize what we said about the tangential component earlier. You can see that the J cap component, when you equate the two, you get that result, that V naught sin theta is equal to VA sin alpha.
Yes.
Here we are getting it indirectly, there we said it directly. So you can compare the two and make that statement. So you can see that MA V naught cos theta is equal to MB VB minus MA VA cos alpha. That's one equation. And MA V naught sin theta is equal to MA VA sin alpha. That's our second equation. So what this is giving us is that VA sin alpha is equal to V naught sin theta, which will in this case become how much? It will become 9.
Yes.
Okay. So there is another logic to this equation. This can also be understood from that fact that tangential component of A's momentum is conserved. Because the collision impulse J is normal in direction. It does not have a tangential component. So that is one additional thing. Okay, so now we are left with what? We are left with, see, we have three unknown things here. Na? But we had four unknown things, theta, alpha, VA, VB. So theta is equal to 37, we've already got. These three are still unknown. So we need three equations. So we got two equations so far. Okay. Now we need one more equation which will come from the coefficient of restitution. Yes, Vedant, that is true only because we have taken the x-axis along the normal direction and y-axis tangential. But the statement that tangential component is conserved, that is a general statement. Okay.
Yes.
So here that tangential component is the y component, so it's working out that way. Okay. So now let's see, we also have the coefficient of restitution equation. And separation velocity, remember, is this, and coefficient of restitution is 0.5. So additionally, we have E is equal to 0.5. It means that separation velocity should be equal to, okay, so separation velocity here was VB plus
VA cos alpha.
VS. So this term should be equal to 0.5 times V naught cos theta.
Yes.
So we have VB plus VA cos alpha is equal to 0.5 into 12. Right. This is like our third equation. Okay. Now we compare this with our first equation. So you can see from equation 1, we have MBVB minus MAVA cos alpha is equal to MAV naught cos theta. So we have 9VB minus 4VA cos alpha is equal to, this term will become 4 into 12. Is it? Yeah.
Yes.
And this equation, if we compare this, VB plus VA cos alpha is equal to 6. Okay. So now to solve these two equations, what we can do is we can just multiply this equation by 4 and add.
Yes.
Okay. So we have 9 plus 4, 13 VB. Cos alpha term cancels. And we have 48 plus 24.
70. Yes.
Yeah, so that's how much? 72.
70.
So that's the value of VB, and from that we'll also get, so VB is equal to 72 by 13. Okay, and now from the earlier equations we have VA sin alpha was 9, and from now here we have VA cos alpha is how much now? We can write this as 6 minus VB now.
Yes.
Yes.
From this equation.
Yes.
Okay. So that is going to be that will be how much? 6 by 13, is it? Okay. So now we know the vectors. We know that VB as a vector is 72 by 13 I cap, and VA as a vector will become minus 6 by 13 I cap plus 9 J cap. Okay, so these are the final velocity vectors. You can see that they are at a obtuse angle with each other, because we have taken y-axis and x-axis like this. So for example, if you want to find the angle between these two vectors, this theta, so you can just use the dot product method, that cos theta is VA dot VB divided by mod VA VB. You just use that method. Okay. So this is the maximum difficulty level of questions related to oblique collisions, which you can get, okay, at JEE Advanced level. So with this, we finish collisions. Now we are looking to wrap up system of particles chapter now. So next lecture, we will essentially solve doubts and discussions. And one small thing which is remaining, which will be variable mass system, including the rocket equation. Okay, if you've gone through H.C. Verma or Resnick, you would have seen that there's an equation for rocket propulsion. So the derivation of that and the applications of that, which will just take a few minutes. So with that, we will wind up the chapter, and then couple of lectures we'll require for doubts and discussions, because lots of different type of questions. Okay. So anyhow, that's it for today's session, people. Wish you all the best. Have a nice day.
Thank you.
Sir?
Samba.
Yes.
So actually I feel that in H.C. Verma there is some in one of the question I feel there is some doubt in that. Means
Just send the question to me better no, on WhatsApp. I'll help you out with it.
yeah, sir. And sir, can you just show the answer those
Sorry,
for
the
a
what?
second?
Which one?
Sir, this one only, the above part.
Acha, okay. This part?
Yes, sir. Sir, can you just scroll down a little? Yeah, sir. Just.
Okay.